guys, welcome to Intermediate Robotics Camp. My name is Shreya and today we're going to be talking about VEX design. So just an overview of this video, we'll be talking about different design aspects of VEX robots such as drivetrains and lifts, and we're also going to look at the pros and cons of different variations of these design aspects. So first we'll be starting with drivetrains, and a drivetrain is basically what makes the robot move, so that includes the wheels, gears, axles, motors, etc., as well as a base structure which is made out of C-channels that can be arranged in different patterns, which you will see in future slides. So there are some factors that you have to consider when choosing a drivetrain. So one of them is balancing stability and reach. Robots that need to reach out farther or higher need a lower center of gravity in order to maintain their balance. So it's important to find a good middle ground between how far or high your robot can reach in terms of its lift, and also keeping the robot stable and making sure that it doesn't tip over when its lift is extended. Another factor to consider is the number of motors. So if your other mechanisms such as lifts or claws, aside from the drivetrain, require a lot of motors, you probably want to minimize the number of motors that go towards your drivetrain because usually there's a cap to the amount of motors that you can use on your robot. Another thing is game pieces and just the field in general. You have to balance between the speed of the robot and the weight of the game pieces that it can carry and the number of game pieces that it can carry. So if you want a robot that can travel fast while carrying multiple bulky cubes, you have to choose a drivetrain that can optimize that. Another thing is the presence of obstacles or ramps. So this is more about the field rather than the game pieces that the robot interacts with. So having tracks can help the robot drive over obstacles. There's a picture on later slides that shows these tracks, but it's basically like how a tank works. And another thing is grabbers. Having arms or claws can influence the drivetrain design that you use because you need space on your robot to accommodate for an arm or a claw in order to grab game pieces from the field. Another factor is to protect your robot against damage or defensive pushing from opponents. And lastly, there's maneuverability, speed, and agility. So this is a square or a standard drive, and it's basically when all four wheels are facing forward, they move in the same direction, and the base of the robot is shaped like a square or a rectangle. It's a pretty basic drivetrain, but it can be useful in games that don't really need complex movements or high agility. And a rectangle can accommodate either a 4 or 6 wheel configuration. So the 4-wheel configuration is the top picture, 2 wheels on each side, and then the 6-wheel configuration is the bottom picture with 3 wheels on each side. And you can also use treads or tracks on this. And again, this is like the tank drive kind of thing. So some pros are that it is easy to build and it also doesn't need as much power, so your battery will last longer. However, this drivetrain can't strafe. And strafing is essentially where the robot can slide around along multiple axes without having to turn first. So let's say your robot was facing forward, it could just slide left without having to turn and face left first. So it's a lot quicker to change directions when you're strafing. So this is a U shape, and the U shape is common when you need an arm or a claw to intake or grab game pieces. As you can see in this bottom picture, the U shape has this gap in the middle, which allows space for an arm and space for game pieces as well. And this chassis can be used with either a 4 or 6 wheel configuration with either 2 wheels on each side or 3. Some drawbacks to this base is that its size can get in the way sometimes, and you can't always get game pieces if they're stuck in a corner. And it's also recommended to use a C channel to stabilize this, because if you just have a plain U like this and you have some kind of mechanisms which are anchored on the back with a heavy lift or game pieces, it's probably going to tip over. The robot doesn't have stability on the front. So this robot right here, it has a lift that's pretty heavy, and it's anchored on the back of the robot. So they use the C channel right here, if you can see my pointer, and that just helps stabilize the whole thing. So this is an H-shaped drive. So the H-shaped drive has 4 wheels that face forward, and what's unique about it is that it has this 5th wheel that's in the middle that faces sideways. So this allows for strafing, but it also doesn't make the code too complex. However, this drivetrain can't go over bumps or game pieces because this center wheel is going to get caught on an obstacle pretty easily if the robot tries rolling over it. And another disadvantage is that you need 5 Omni wheels with 5 motors. So if you have a lift that needs a lot of motors, you're probably going to be at a disadvantage because this drivetrain requires an extra motor. But what's cool about this drive is that it has these Omni wheels. So when it's going forward, the beads on this Omni wheel, on the center Omni wheel, allow it to go forward because the beads roll this way. And when the robot is going sideways using only the center wheel, the beads on these outer wheels go this way, and that just reduces the amount of friction that it has, and it allows it to strafe pretty easily. So this is a tank drive, and it can be used with either normal wheels or with treads and rollers. So in a tank drive, the left and right sides of the robot are controlled separately. So when you're turning the robot, one of the sides moves forward and the other moves backwards. So in this diagram, the right wheels are moving forward, the left wheels are moving backwards, which allows it to pivot left around its center. And the main advantage is that this drivetrain can get over bumps pretty easily, especially when you're using treads. So these rollers, they can like fluctuate up and down. So when you're going over some kind of obstacle, it's pretty useful. But some cons of this drivetrain is that it can't strafe, so it can't slide in whatever direction you want, and it's usually slower than other drivetrains. So this is a holonomic drivetrain, and in this drive, the wheels are set up in an X formation, as shown in these pictures. It can travel in all directions and is super agile while strafing. However, the complex movement of this drivetrain, as you can see in this diagram, makes it hard to code because all of the wheels are angled, so you have to account for the different motion that all of the wheels are going in when you're actually programming the controller. And it also can't get over bumps easily because, as you can see, it's pretty bulky and flat to the ground. This is a Mecanum drivetrain, and it uses Mecanum wheels, which is shown in this diagram. And these Mecanum wheels have these angled rollers all around them. It's kind of similar to the Omni wheels, except that there's no beads and the rollers are angled. So when the wheels on this drivetrain rotate opposite to each other, the roller's orientation causes the drivetrain to move sideways. So it's kind of similar to the holonomic drivetrain because it allows for strafing and increased agility, but the wheels they don't have to be angled and they don't have to be like on the corners of the robot. They can still face forward, but the angle of these rollers allows it to kind of have the same motion as a holonomic drivetrain. However, some disadvantages are that it needs more power from the motors to power the drivetrain, and it also needs more complex code in order to move properly. So now we can move on to lifts. So lifts are just anything that can elevate a game piece or claw or whatnot. So first we have bar lifts, which use rotational motion to rotate an arm, which is usually made of C-channels, in order to reach high places. So objects which are attached to the lift usually rotate in an arc-like motion, which results in the attached mechanism to reach out as it gets higher. So bar lifts are pretty simple in design, and they have multiple variations, including 2-bar or swing arm, 4-bar, 6-bar, 8-bar, and chain bar. However, they do have relatively low reach compared to a reverse bar lift or scissor lift, which I'll talk about later. However, stacking more bars above your existing lift can increase the reach. So just to demonstrate how a bar lift moves, so looking at this swing arm, it moves in this circular motion. And then for this 4-bar lift, it just moves up and down in the same way, but there's also these bars here which provide extra height. So things like claws can be attached to the ends of these lifts in order to grab game pieces. And keep in mind that there are different versions of each of these lifts, and the diagram only shows one way to build them. Like different teams may choose to build 6-bar lifts in different ways. So for a 2-bar lift or a swing arm, it's pretty simple. It's more suited for lightweight loads. For a 4-bar lift, it's more common. It does have a higher reach because more bars means more reach, and it can carry light to moderate loads, I would say. And then for a 6-bar, it's probably the most common bar lift, and it can carry moderate to heavy loads, and it has a pretty high reach. Now, 8-bar lifts have a very high reach, and the main disadvantage of this is that the amount of bars can get complex to build and navigate with, and it's not as commonly seen in competition bots as these other lifts. And then lastly, we have the chain bar lift. So the one shown here is kind of similar to the 2-bar, but it uses a chain, which is gray here, and then these red sprockets so that as the arm rotates up, being powered by this motor, the object at the end of the arm also rotates simultaneously. So for reverse bar lifts, they allow the robot to reach higher than a typical bar lift, and they lift objects that are attached in an almost vertical motion. So they are more difficult and time-consuming to make, but they can be more beneficial in some cases. And some common variations of reverse bar lifts are the double reverse 4-bar, reverse 4-bar, and reverse 6-bar. So on this slide, I included two pictures of a double reverse 4-bar because these are the ones most likely seen on competition robots. So as you can see in this one that's unextended, it starts out bended backwards as compared to the other bar lifts, which start out facing forward and they move up and down. But this one starts out bended backwards. And the reason it's called a double reverse 4-bar is because it has two of the same exact lift that are attached to each other and move simultaneously. So this doubling of lifts allows it to have a lot more support, and it's able to carry heavier pieces. And the double reverse 4-bar lift has a lot of reach, and you can see it in this picture. It can reach really tall heights when fully extended. So elevator lifts are another type of lift, but they use linear motion, and they use linear slides that extend vertically, and they're pretty compact and they don't take up much space on the robot. But the main limiting factor for elevator lifts is the friction that can slow it down. So one type is the rack and pinion lift. So the rack, which is basically like a gear which isn't circular and it's like a straight line almost. So the rack gets attached to this linear slide, and the pinion, or the gear that is powered by the motor, gets attached to the rack. And the pinion rolls up against the rack and uses the motor's power to move the slide up. So this is another type of elevator lift, but it's a multi-stage extension lift. So the motor rotates the chain, which the linear slide is attached to, which causes the linear slide to get pulled up and down by the chain. So in this picture on the left, you can see how it looks unextended and extended. And on the right, you can see how linear slides are used in an actual competition robot. And just like other elevator lifts, it's compact vertical motion. Lastly, we have scissor lifts, which are really common in VEX robots, especially when you have a game that involves towers and placing game pieces in high places. And they allow the robot to reach high places with a series of C-channels. So each pair of C-channels is attached at the center to form an X shape, and each X shape is called a stage, and these stages are each attached at the end of each other and stacked upon each other. And because of these stages, scissor lifts generally have the highest reach out of all the lifts. So they're good to use when the game involves tall towers and dropping game pieces in elevated containers like shown on the right. However, they are pretty difficult to build and they need a lot of material because you need to have all of these C channels and all of the screws to stabilize and make the scissor lift work in general. And another disadvantage is that they can become unstable at higher levels and cause the robot to tip when extended. So this is unextended and this is fully extended. And this is where the drivetrain comes into play. You need to make sure that the drivetrain is able to support the scissor lift and not tip over when it's fully extended. And these are the sources that I used. Thank you for watching. Bye.